This section explains the Deep Deterministic Policy Gradient DDPG model and code implementation. Let's first look at the DDPG model overview. Deep Deterministic Policy Gradient is an off-policy reinforcement learning algorithm designed for continuous action spaces. It combines the Deterministic Policy Gradient (DPG) method with deep Q-learning and uses Actor-Critic architecture to model both the policy and value function. Actor-Critic approach DDPG uses two neural networks. Actor determines the policy, mapping states to actions. Critic evaluates the quality of the selected actions by estimating Q values, where phi represents the parameters of the critic network. DDPG works efficiently in environments with continuous action spaces. Mathematical foundation. DDPG operates within the framework of policy gradient methods and Q-learning. Let's break it down. Policy gradient. The policy gradient theorem gives the gradient of the expected return j theta with respect to the policy parameters theta as follows. QSA is the critic's estimate of the Q value for state action pair. Mu is the actor's deterministic policy for a given state S. The gradient of the expected return is used to update the actor's parameters. Bellman equation for Q-learning. The Q value represents the expected return starting from state S, taking action A, and following the optimal policy thereafter as follows. R is the immediate reward for taking action A in state S. Gamma is the discount factor that models the importance of future rewards. Q prime is the future Q value at the next state S prime for the action A prime. DDPG uses the deterministic policy, so the next action is given by as follow, where mu is the actor's target network. Target networks and soft updates. To stabilize training, DDPG uses target networks for both actor and critic, which are updated slowly using a soft update rule as follows. Theta A prime are the parameters of the target network. Theta are the parameters of the main network. Tau is a small constant, soft update parameter, typically in the range of 0.001 to 0.01. This ensures that the target networks move slowly, which stabilizes training by preventing drastic changes to the target Q values or actions. Architecture of DDPG. DDPG uses the Actor-Critic framework, and each component has both a main network and a target network. Actor network takes the state S as input and outputs the action A. The output is bounded between -1 to 1, using the tan activation function, as the action space is continuous but constrained within these limits. The actor's loss function is based on the critic's value as follows. Critic network takes the state action pair SA as input and outputs a Q value. The critic's loss function is based on the Bellman backup as follows. Target networks. The target actor and target critic are updated using the soft update rule. Now we implement the DDPG code. Actor class. Critic class. Replay buffer class. DDPG class. Testing the DDPG model.